Alright, let's do the YouTube intro and then we'll have a video, alright? Alright, welcome back everyone. So today is the review stream for the JMO and USAMO 2021, so the American National Math Olympiad. I'm going to be showing you the solutions to all 9 of the distinct problems that showed up. For anyone that's curious, these are the problem authors, so congratulations to all these authors for getting a problem and thank you for your contributions. Writing a problem for this test at all, like even having a problem to submit is already a lot of work. So we're very grateful for everyone's continued contribution. Okay, let's get started. So why is Oncon just Oncon? Because we all know who he is. Okay, so JMO1 is a functional equation. It's like you want to find all functions that satisfy this random constraint. So spoiler, the answer is just f equals 1. That's it. There's no interesting functions that satisfy the condition. So let me tell you like the way the proof goes. So we're going to first say like f of 1 is f of 1 squared. That's clear. So you get f of 1 equals 1 pretty easily. Now if you plug in like a equals b equals 1, you get f of 2 is f of 1 squared. So f of 2 is just equal to 1. But f of 3 is like the first time where you can't just like straight plug something in. So let me tell you how you get f of 3. And once I tell you this, you'll see like the way they go from here. The way you get f of 3 is to use the magical fact that there's a Pythagorean triple. 3 squared plus 4 squared equals 5 squared. Sorry. Yeah. So this is true. And this is equal to f of 5 all squared, which is f of 2 times f of 1 all squared. On the other hand, this thing is equal to f of 3 f of 4. So because this whole thing is equal to 1, and the codomain is positive integers, this is 1, and this is 1. So that's how you get f3 and f4. Okay, so more generally speaking, if you have the following characterization, f of a squared plus b squared squared is equal to f of a squared plus b squared all squared is f of a f of b all squared, is this thing is equal to a squared minus b squared all squared plus 2ab all squared. This is sort of like a parameterization of Pythagorean triples. It generalizes to 3, 4, 5. So anyways, this is equal to f of a squared minus b squared times f of 2ab. So if you know that this a priori that this is equal to 1 and this is equal to 1, that would imply that these two are also equal to 1. And that's basically good enough for the induction, because what happens is if you know f of 1 through f of n, say, are all 1, then f of 2n plus 1, or let's say f up to 2n, f of 2n plus 1 is equal to f of n plus 1 squared minus n squared, and f of 2n plus 2 is like f of, I guess like 2 times 1 times n plus 1. Evan, what do you think winner will be? I don't know yet. I have a guess, but I don't know. I haven't been watching AOPS at all, so I don't know what people are claiming. Okay, so that completes JMO1. Like, this induction is the whole thing. Alright. What order should I do this in? Do I just do all the JMO only problems first? I think that makes sense. Let's just do all the JMO only problems first, in ascending order of difficulty, and then we'll move on to the actual USAMO problems. Nose was a mistake. Yeah, every time I run one of these review things, that's what I think to myself. Okay, for JMO4. So you have these 3 pins at A, B, and C, and you're allowed to move them by like 1 distance, and you want to make a triangle that has area 2021. So let me just look at a generic position of the pins. Let's say you have something like this. Yeah, this problem is Brandon. So we're doing all the JMO only problems first, and then we'll do the USAMO and 142.536. So we're going to define the bounding box to be like the axis the axis aligned rectangle that of smallest size that contains all the points. So this is called a bounding box. And claim area of bounding box is area of the triangle is at most half the bounding box. This is not too hard to prove. You can prove it just by doing straight coordinates, or alternatively, a slightly weirder proof goes like this. Like, you take this point C and you imagine varying it along these 2 things. Because the area is linear in C, the extremes will be reached by the endpoints, and then you can check it at the endpoints because then it's 1/2 base height in both cases. So anyways, this claim is true. On the other hand, the bounding box width plus height increases by at most 1 per move. So every time you make a move, the bounding box might not change, but if it does change, it increases by at most 1. So therefore, if you make n moves, your total area is at most n over 2 squared by AMGM, because the width plus height will be at most n. Moving pins, yes. This is a moving pins problem. Okay, so this will immediately imply that n is at least 128. Because this will, if n is less than 100, if n is 127 or less, the bounding box won't be big enough. Okay, so that's the lower bound. On the other hand, the 128 is actually achievable. And the way you achieve it is to, let me just pick some coordinates. Well, okay, let's do it this way. 64. If this is 0, 0. Oh, freak, I need to shift it. Alright, I'm gonna translate it slightly. Well, okay, no, I'm not going to translate it. Screw it. This is easier to the right. 18, 64. This is 64, 3. So if my bounding box is really 64 by 64, then from this point, 18, 3. Yeah, that should work. So if you do this, so I've shifted it, so rather it's starting at 0, 0, I'm starting at 18, 3, and then looks like that. So this will be indeed give you exactly 128 moves. On the other hand, the area that you get here by shoelace is equal to 64, 3, 18, 64. So I've rigged these constants so that this gives you exactly 4022. Sorry, 4042. Okay, so that should work fine. That's a construction. Yeah. Okay, so that's it. Okay, so now let's go on to JMO 3, which I think people are more interested in. So the first thing I should say is that the bound is the bound is sharp up asymptotically. I don't think it's sharp up to like exactly. But like there are pictures for which you get something close to. All right, so let me put this picture up because this is useful. Yeah, I don't think the linear part is in here. But on the other hand, so this tiling exists. Looks like this. So this is going to break a lot of wrong solutions, I think, because a lot of people try to argue that like the you know, it's sort of just the straight alternating picture, but it's not. This is actually the asymptotically tight shape. Okay, so anyways, let's prove the bound. So basically the claim is as follows. Alright, look at any downwards equilateral triangle. This solution I think was given by Andrew Gu, to give credit. This is not the author's original solution. What we're going to do is we're going to construct a hexagon that looks like this. So for every downwards equilateral triangle, I construct this hexagon. Okay, claim the hexagons disjoint and lie inside delta. This is true. You can just check it. Okay, so because of it, you get an area bound. Because the area of this thing is, what is it? So this is like 1/2 3/3/8. I think. Did I get that right? Probably got it wrong. That's why I should just read my notes. Okay, cool. No. Yeah, that's fine. Okay, so 3/3/8 times n is less than or equal to √3/4 L squared. So n at least 2/3 L squared, the end. Yeah, you can shift the hexagon if you want. That doesn't really matter. This one's a little easier. This is like the sharpest one for which it like lies inside the It's a little easier if you do it this way to show that they lie inside the big triangle. Yeah, 3/2 equilateral triangles. Yeah. After you finish the problems, will you say which problem goes where? Maybe. Yeah, I think realizing this shape exists helps a lot with the proof, because now you know, you can see the hexagons in here, really. I know. You can kind of see them. Yeah, there's other shapes you can draw that will work, because like, you know, but basically this is sort of the general gist. Alright, cool. Let's go on. So USAMO 2021-1 is a geo. So I'm curious whether like there's any solutions to USAMO 1 that aren't the official one. Yeah, this problem is a bit of a art school. I think all the solutions today are going to be quick. I think every problem is like pretty quick to carry out. Alright, so you have these rectangles. Anyways, the angle condition tells you something. It tells you the circumcircles of rectangles are concurrent. That's sort of what the angle condition does. So if you take one circle and then a different circle, these two angles will add up to this last one. Let me use a highlighter or something. That will work. So this is exactly what the angle condition says. It's like when you take two intersections, the third one lies on there. Okay, what does that do? Well, now this angle is 90 because it's a rectangle. Also, this angle is 90. So it lies on one diagonal, hence lies on all three. The end! Bryan-Con's theorem. Okay, so now let's do Carl's problem. Oh, is it Bryan-Con? I have no idea. Okay, USAMO 4. Okay, so the answer is S should be a power of 2, or if you are a keeper of the empty set, I guess S equals the empty set works as well. Technically. We're doing 1, 4, 2, 5, 3, 6 is the order. Oh no, if people mess this one up. Well, empty doc, I really hope not. But also, like... yeah, I mean, I don't know what to tell you. Okay, so let me tell you what the construction is. What you do is you take primes. Oh, let me write multiplication actually. You take like two E distinct primes. And then you look at all 2 to the E products of this form, so P1 or Q1, P2 or Q2, etc. Okay, this just works. You can check it. If you take, like, say, without loss of generality, look at the element that's all the top row, then, for every GCD, you flip the corresponding ones. Okay, so now let's show the bound. Or, not the bound. So, let's suppose you have a hypothetical element n equals, like, P1 to the E1 times... let's just do P to E, actually. Times... blah. So other stuff. Where E is greater than 2. I claim this is impossible. Alright, and here's why. So on the one hand, if you look at the divisors of n, you see that, like, by taking the GCDs, you get, like, a lot of things are divisible by P, right? Like E over E plus 1 of the elements in S has a P in it. Okay, on the other hand, let's take any M such that VP of M equals 1, which you can do because you take something that has, say, e.g., among other things, GCD M comma N equals P would be good enough. Okay, now if I look at divisors of M, we see that M has VP equals 1. So the elements of S line up with the divisors of M. Half of them are divisible by P, half of them aren't. So 1/2 of S has P. I need to scroll down. Okay, so these two things are equal. So this implies e equals 1. Yeah, that's it. How do you get the construction without solving? Yeah, I don't know. I feel like if you get the construction for 4 things, like, you kind of know what's going on. Like, 4 I think is big enough for you to see the general situation. Yeah, also if it's square free, this answer is certainly powers of 2. If you can show it square free. Alright, let's go on to USAMO 2. This one actually might be easier for me to, because I have diagrams prepared for this one. Alright, so I put the planar version. I just gotta say, God, the wording this problem was such a nightmare. We still didn't get it right, even after that. I'm whatever. Actually, no. Let me keep using the board. Yeah, it really should have said any particular junction. Yeah, I want to say, do you know how annoying it is to be just all these papers that have these like 40 vertex graphs on them that just going left, right, left, right, left, right, and it's just like drawn with no labels. Yeah, I think I think what we should do is make an art gallery out of all the wonderful constructions that people managed to invent on this problem. Anyways. Yeah, I think the thing is, if you interpret any junction as like the length of a path, like the problem is obviously not functional, right? Like there's no way the length of the path will be ever bounded, like, period. Okay, so there are many constructions. Like there's so many that like, this is probably the simplest one that is explicit. There's other ways you can make it smaller if you're willing to like truncate things. Like if you draw a vertex of degree 1 and then don't draw the stuff adjacent to it, that's fine. I think this is like the smallest self-contained example that I saw so far. Where if you go like this, it should work. Okay, so let's prove the bound. Oh, I should say the answer. Yeah, answer 3. Yeah, the planar is only there so that left and right makes sense. Otherwise, it doesn't really matter. So, the gist of the proof is as follows. So at any vertex, there are a number of possible turns, right? So really there's 6 possible turns because you can go in from one of 3 ways and you can either turn left or turn right. So and then the opposite ones. So there's 6 turns, and a turn uniquely determines everything else. What I mean by this is like, if you know, for example, that the visitor turns like this, if you know this turn shows up, ew, what is that? That's not a highlight. Good. Then it uniquely determines the rest of the path. So this automatically implies that you can't visit more than 6 times, because if you it tells you that the trajectory is totally periodic, not just eventually periodic, because it determines both before and after. So, totally periodic. Trajectory. So this will give you a bound of 6. However, I make the following claim, which is that you can't have both this and that. So claim no ABC plus CBA can occur. Thank you, Boff, for the follow. And the reason is that, well, I actually have a diagram prepared for this. Maybe I'll just post that one. Okay. Shoot. Yeah, so here's a diagram, which is basically why you can't. So if you had a turn here and the same turn here, when you trace out what happens next, you find that these two paths are always like, you know, doing the same thing, going back and forth in the same way. And so red and blue paths here will, red and I guess the backtrack of the blue path will never meet. Contradiction. So hence at most 3 visits to each vertex. Yeah, so the proposer mentions a couple things in their comments. It is an old folklore problem, not very famous, but it is known to that the total periodicity, that is the past problem. You can find that in like old Moscow Olympiad and so. Yeah, I forget exactly what year the reference was. The other is that in fact you can get graphs for which you visit like 99% of the vertices 3 times in your trajectory. This was not Oncon. The author of this problem is Zoran Sunik. Yeah. Okay, cool. Which Russia problem? I don't know the exact reference. I remember it was... It's like old. It's like before 2000s. But I don't remember the exact reference off my head. Alright, we're on a roll. Alright, let's do the giant system. Okay, so here's a system of equations. The answer is exactly what you think it would be. The only answer is 1, 2, 1, 2, so on. All right, so here's the proof. So we're gonna do Andrew's proof, right? So we're going to look at the min and the max across all the numbers. There's a sense in which positive reals is important, right? If you want to solve this system with our complex numbers, you're dead. Like, you can't solve a system like this over the complex numbers because you know that you'll get some high degree polynomial, and that polynomial will have, you know, however many complex roots it does. So the fact that the problem is asking for positive reals is really important. Like, it tells you that you're supposed to use something about the fact that it's reals and not complex. And the way we're going to use it is we're going to use this min and max. Okay, so if you look at the indices that reach the min and max, so you know there's an index that's called the index I, right? That gets the... So I'm looking at just the even ones because these equations are sort of stupid. Yeah, like I'm just gonna go... You can eliminate half the variables at once. I guess it doesn't really matter which ones I eliminate. Let's eliminate the even ones for the sake of my narrative. So we're going to just get rid of the equations on the left right away and just plug those in. So the equation looks like this for even indices. we take the min and max, and you get a statement that looks like this. All right. Why was n at least 4 stated? Oh, it's because we were worried that because the equation's actually right up to 7, right? Like, it's explicitly given up to 7, so if n is less than 4, then some degeneracy occurs in which the statement doesn't technically make sense. I mean, obviously, what you're supposed to take the indices mod to n, but like, yeah, it's just there. Yeah, don't read into it. It's just there so that the 7 doesn't break things. Okay, where was I? Alright, so the natural thing you might try to do is bound these by the little m to get some inequality on little m, but actually it will be better for us if we use capital M as our bound. So this will be at least 2m plus 2 over capital M. The reason is that this is now symmetric in little m and capital M. So if I do the same thing on the other way with whatever index achieves the min or the max, this will be less than or equal to 2 over m plus 2 over capital M. Okay, so m at least 2 over m plus 2 over m at least m. So min at least max, and hence m equals m. And yeah. So now they're all equal. That's it. Yeah. Solution credits to Andrew. Show the Algmanip solution. Which one is the Algmanip? The one where you do like the random Cauchy-Schwarz? I think this thing is not that unmotivated. This is a thing that you do a lot with. Okay, fine. I'll show the Cauchy-Schwarz. So first of all, sum of AI is equal to a2i. If you do straight sum here, sum of a over 2i is equal to sum of 4 over... what am I saying? The sum of the numbers is equal to the sum of 4 times the sum of the reciprocals. On the other hand, if I take this equation and divide it by a over 2k, then I will get the summation, which is... freaking... 1 equals a2k squared, a2k. So this is true. And the reason for writing it this way is because now when I take the sum, this thing works out pretty well. This thing will be exactly equal to the sum of like 1 over a 2k minus 2 plus 1 over a 2k squared. Okay, and obviously the left-hand side is exactly n. So what happens is this thing gives you a lower bound on the sum, because by Cauchy-Schwarz, the product of these two things is at least like n or whatever. On the other hand, this thing, if you apply Cauchy-Schwarz, if you use like Cauchy-Schwarz or QMAM to get rid of the squares, it will give you a upper bound. Yeah, it will give you an upper bound on the sum of 1 over 2i. So the top one gives you a lower bound on... In fact, let me just call this S, alright? The point is this thing is at least like... oh crap, I'm gonna mess this up. S squared over 1 over n or something? I don't know what the constant is, Jesus. What do I think S is? We think S is 2n. 4n squared. Left hand side is n. 4n. Okay, whatever. Whatever the number is. So now you have both a lower bound and an upper bound on s. The upper bound because s squared is at least n squared times 4. So the upper and lower bound match, and that will force all the numbers to be equal as well. So this is sort of the algorithm solution where if you do this division exactly, it will come out to an inequality. I honestly think this one is more motivated because, like, I don't know if you've seen, like, there's problems with the form. You know that problem that's like, you have a graph and, like, every vertex has a number and that number is the average of the neighbors, and show that every connected component has the same number. And, you know, you look at the min and the max because those are the ones that will cause the most problems. I think it's reasonable to want to try that here as well because you have a... You know size matters because it's positive reals. You cannot solve this system of equations over complex numbers. And consequently, if you look at the min and max, then all you need to do is make the right observation that this thing actually is 2 over m. Like, the first thing you'll probably try is to bound this above by, like, 2 over little m, and you get little m less than or equal to 2 less than or equal to capital M. But if you flip it this way to get a lower bound on little m, that's the direction that will work. Algmip is cool? Okay. I don't know. I'm not an algebraic manipulations person. I don't know how to motivate them. This one is at least a little conceptual. It's like, this thing automatically gives you a lower bound on the sum, so if you can get an upper bound on S, you're done, because the upper bound will match at the equality case. So, you know, that's your upper bound. Yeah, IMO 2018 too is a different problem. That was something like that. Okay, let's go on. Alright, so this problem. Okay, so you can do this some random operation, and it's pretty easy to see that for n equals 3, the goal is achievable, because what you do is, let me just draw a picture. Oh, frick, no! I forgot the fragile option. Ah! We're doing it live. Which means that I get to screw up things. Okay. Thank you, Fort Nalka, for the follow. Yeah, this is really the reason this is considered politically correct to have on the same day as the other combo problem is because the solution is actually algebra. Alright, so I think the problem statement is not important because you guys know what the problem says by now, so let me just move it. But here's a construction for n equals 3. So you put 2 L's, clear this row, do that, clear them both. So consequently, consequently you can also do it for any multiple of 3 by just repeating this pattern. So we are only going to pay attention to showing that n does not divisible by 3 will all fail. And the big thing about this problem is I'm going to relax. There's a condition in here that you can't place a stone on, you can't have more than one stone per cell. We're going to ignore it. So ignore less than or equal to 1 stone constraint. We're not going to use this constraint for this direction. Also, we'll even allow real weights. Like, you can apply the operation a fractional number of times, and it's also okay. So this is a big leap of faith. I'm like just saying I'm going to throw away a bunch of conditions that could have been used. Was your solution to one involving circles? Yes. Yeah, so the 0, 1 is not necessary. That's what I'm about to say. Like I'm just going to throw away all of the combinatorics. Oh no, your solution had no circles. Okay. Okay, so what's going on? In the problem we have, if you let p of xy, so we'll do generating function in the following sense. So this is the x to the 0, y to the 0. This is like x to the 0, y to the 1, da da da, up to like x to the n minus 1, y to the n minus 1. So our operation corresponds to polynomial p such that degree of p is less than or equal to, let me write this all. Degree x, degree y, n minus 2, n minus 2, and we have 1 plus x plus y times p of xy. So basically, like, you can pick anything that's not in the topmost thing, and it's like, you know, x to the a, y to the b, x to the a plus 1, y to the b, x to the a, y to the b plus 1. That's what we're going to do. Evan, what if I screwed up the degrees? I don't know. Oh. Good luck. Alright, so the point is that this thing apparently corresponds to something where I can clear all the rows and columns. So it means it's in like 1 plus x up to x to the n minus 1 times something, some y polynomial. We'll call it blah of y. I want to emphasize it doesn't really matter what it is, honestly. It can even have other stuff mixed in. So a successful clearing corresponds to a non-zero polynomial p such that this is true. So p tells us where to place the Trominoes, and this thing on the right tells us where to clear rows and columns. Again, I don't care at all about the less than 1 stone constraint. I'm doing everything with real multiplicity, and it's okay. Okay, so what we're going to do is we're going to plug in x equals nth root of unity, which is not equal to 1. Y is also equal to the same thing. So when I plug in such a number, this thing equals 0 and this thing equals 0. Also, because 3 doesn't divide n, this thing is never 0, because the only way you can have roots of unity that sum 3 roots of unity that sum to 0 is if they're an equilateral triangle or whatever. I said your name wrong. Oh, I'm sorry. Okay, so cool. So what this means is that p of xy is vanishes on a lot of stuff, right? Like p of xy is equal to 0 for, oh crap, I'm out of space. Let's zoom out a little bit. P of xy is equal to 0 for all xy in like s times s, where this is a set of size n minus 1. Namely the roots of unity. Okay, on the other hand, this contradicts this thing. If you really want to be highbrow, you can quote combinatorial no-Stellensatz, but really what happens is polynomial with bounded degree in x and bounded degree in y can't vanish on an larger than degree by larger than degree grid like this. Thank you, Cho RMHU, for the follow. It's not really combo null. Combo null is stronger because combo null can work even if hang on, what's the condition? combo null can work under weaker conditions. Combo null is you take a term of maximal total degree, and you can take sets of size larger than the exponents. What I mean for this is like, here, let me give an example. If your polynomial p had was like equal to x cubed plus y cubed plus x squared times y to the 4, you could apply combo null to a 4x4 grid by using the fact that this monomial is non-zero, but you can't apply just degree bounds, like, because this is degree 4. So combo null promises you can use that term. And for this particular problem, the degree condition is so strong that combo null works for any term. But combo null is a little more precise than that. Yeah, so the manual proof is you plug in a value of, if for a fixed value of y, the degree is small enough that all the coefficients are 0, so the coefficients, which are polynomials in x, are now 0 at n points, n minus 1 points, and then it kind of burns. But basically, it for degree reasons, it doesn't work. Like, the degree conditions here are actually stronger than what you need. I kind of dislike this problem because of the fact the idea is somewhat well known. Okay. I don't know. Some people don't get it. I mean, I don't think anyone will be surprised like at all if we can find like there exist other Math Olympiad problems where you use roots of unity weight, right? Like that's just like a technique, and I think it's fine, right? Like I think I would be annoyed if it was like, because it's well known, a bunch of people just solve it because without having to think. But I don't think this problem is such a problem. Evan Mohs ratings? I don't know. I'm gonna wait until I see. The Mohs ratings will go up on my website eventually once I decide how hard I think the problems are. But I want to see the scores first. I went into grading thinking that the scores were going to be pretty high, and now I don't think the scores are going to be pretty high. What do you think the difficulty order is? I think it's for USAMO. I think it was about right. Do I hate Geo? No. Like, I think if I was a contestant, it would be 142536 for me. Well, okay, maybe I would have thought 5 was easier than 2. I'm not sure. But I'm just bad at algebraic manipulations in general. Whereas 2 is a little more conceptual. Alright, let's do the Hexagon Geo. So we're going to present the black magic solution, alright? So I'm going to put a diagram. This diagram is deliberately not to scale. It only has the parallel condition used, and I don't make the side condition. I think if I draw it this way, it is easier to see what is going on. So this diagram is not to scale, deliberately. It is all a metaphor. What we're going to do is we're going to draw parallel lines in red through A, C, and E, parallel to the opposite sides, and same for in green for B, D, and F. Let me make this a little bigger actually, and take the whole screen. So red, green. Oh crap, that's too big. No, get back. Okay, so these two triangles you can very quickly check are congruent because the lengths are equal to like the differences of like these things, blah blah blah. Also, like X is the midpoint of AD, is the midpoint of MN. That'll be relevant in just a moment. Here is the beauty, alright? Claim AC, if AB times DE equals BC times EF equals CD times FA, then ACE and A prime, C prime, E prime have the same circumcenter. And the reason is that the power of the point, let's take the point C, okay? What is the power of C with respect to A prime, C prime, E prime? It is given by this length here, which is the bottom, times this length here, which is AB. So this length is always equal to AB times DE. So consequently, if these three things are all equal, ACE all have the same power. So they lie on the same, they have the same distance. Okay, so now if they have the same circumcenter, then it's enough to show that the circumcenter of A prime, C prime, E prime, the circumcenter of B prime, D prime, F prime, and the orthocenter of XYZ are collinear. So why have I drawn X here? It tells you that X is the midpoint of this midpoint and this midpoint. So XYZ is like the average of the medial triangle of this red thing and this thing, this green thing. So XYZ is the average of the medial triangles of A prime, C prime, E prime, and B prime, D prime, F prime. And therefore, its orthocenter of XYZ becomes, because the orthocenter of the medial triangle is the circumcenter of the reference triangle, that tells you, in fact, this orthocenter is the midpoint of these two circumcenters. End proof. I will say, this is not the author solution. This was found by contestants. We were looking, we were combing through the problem 6s, and we saw the solution, and we were just like, holy crap. Yeah, we're done. That's all 9 problems. How fast will grading be? Problem 3 and problem 6 are very easy to comb through. Most of the solutions are obvious zeros. The official solution is something like slightly longer. The official solution goes along the lines of like showing that the medial triangles of ACE and BDF are concyclic, or the 9-point circles of triangles AC and BDF turn out to coincide, and also the circumcenter coincides with the circumcenter of XYZ. So it's like similar in spirit, but it's a little less compact. Yeah, but I think this one is like the cleanest way of presenting it, because it's just like the solution is almost shorter than the problem statement. Evan, is this bashable? I don't know. Evan, are you allowed to say if you think... Oh, I am allowed to say, and right now I don't really know. Because I actually haven't even been looking at AOPS, so I don't know like what kind of scores people are claiming. It will be a while. I probably won't look at AOPS at all for a while, honestly, because I don't want to figure out whose solution is whose. But yeah. Well, you'll see. I don't know much either. I know less than you guys do because I'm not watching the forums about what the scores are going to look like. Yeah, I mean, if you do the 9-point circle thing, then like a chess match. What Otis unit is this problem? I don't honestly. I was thinking about Weird Geo, but I don't think it really works that well. It has a little more, yeah. I think it would be better in G6 Summit than Weird Geo. Yeah, I don't think this quite fits Courage. It's such a setup problem. It is, yeah. Does Evan check Discord? Sometimes. I get a lot of messages, so it's hard for me to keep track. If you have something actually important, you should email me instead. What's your email? Look on my website. It's just there. Alright. Yeah, I think it's a little too synthetic for Weird Geo, is my feeling as well.